Today's lesson, section 3D-C, we're talking about cylinders. Okay. Now, usually you would think of a cylinder as something that kind of looks like this. Okay. Now, that is one of the cylinders that we can talk about, but it's not the only cylinder. So our cylinder family will get a lot bigger with this section. Okay. So to describe a cylinder in 3D space, let's say let C be a plane curve, okay, and then let L be a line intersecting C that is not in the plane of C. So what that means is I try to draw a picture here. So C, when they say is a plane curve, so it's a curve in its own plane. So now they don't really have it displayed here, but imagine this curve being in a plane that's completely vertical. Okay, so like a sheet of paper, straight up. And during class, I think I have a pretty good way of showing you this. So hopefully I can, if you don't understand this visually right now, then maybe I can help you during class. So imagine C in a plane that's vertical, and it's just a curve, so it's like its own equation or whatever. Okay, and then this line L kind of intersects, so it comes at it horizontally, so it's at it coming at a different direction. And so it intersects C, and it can do that at any given point. So what they want you to think about is, like, if L moves around, so this next part says the set of all points on the lines that are parallel to L and that intersect C is called the cylinder. So L has many different other lines that are parallel to it, so then let's put all those lines together, and then that creates this plane that intersect, or all the intersections of L with C. Okay, so kind of think of that L line that just moves infinitely around on C's curved line, and then creates a plane by doing that. So that's what that red picture is trying to represent. Okay, so that's a definition of a cylinder. So that makes it so cylinders can be really anything. So they don't have to be a closed shape that just has like an open circle in the middle. Okay, it can be a shape that's not closed or doesn't connect to something else. So you can involve your parabolas, your hyperbolas, your ellipses to these, and then all these other kind of planes. So any other equation would really work to make a cylinder. So then, cylinders occur naturally when we graph an equation in 3D that involves just two variables. So any equation that we did in 2D is now, if you just keep it in and change the dimensions to 3D, now it's a cylinder. Okay. So like this example, I have a hyperbola equation here for the general form. So I don't have A or B, but generally, if it was just graphing, it would look like this. Okay. And so hopefully this picture kind of makes sense. I did it also on the grapher, the 3D grapher, so that you could see it. And so notice how you get the hyperbola shape here and here, and it extends all the way down and up, but now you have like a plane. So it's kind of like taking a piece of paper and just taking that outline of, like, if you looked at it straight on from the bottom as you curled it up to make a hyperbola or a parabola or whatever, but then you looked at it in 3D and now it's fully extended because it's including all those values from the missing variable. Because when you don't have a variable, so like this one's missing Z, when you're missing Z, that means Z can be whatever it wants to be. So then now if it's a million, it doesn't change your equation. Your equation's still correct. It's just now Z is 100 and a million, or -5, or -1/2, or whatever. Okay, so it could be whatever it wants to be. So that's what creates that look, that surface. Okay. So example 1 wants us to be able to identify the cylindrical surfaces, and then the axis to which its elements are parallel for the following. So we need to identify what kind of surface it is, and then which axis it's parallel to. So looking at this, I have x squared plus z squared. I'm not concerned with the numbers, but that would mean that it's an elliptical or ellipse shape. So then there would be an elliptical cylinder. Okay? And then because y is not here, it's missing, so then your shape is going to be parallel to the y-axis. Okay? And then looking at the next one, letter B, you have a y and a z squared, so one is squared, one's not. So that means it's a parabola in 2D, so that in 3D it would be a parabolic cylinder. And because x is missing, then that means it's parallel to the x-axis. Okay? So now I want to be able to graph, and then they want you to label these. So here I just want to put my equation into standard form so it's easier to understand. So dividing everything by 27. Okay, so then that gets me x squared over 9 minus y squared over 1 equals 1. And so then now I'm just going to graph this like I would normally in 2D, but then you just have to add the extension of whatever axis you're parallel to. Okay, so if x is squared over 9, so then your a value is going to be 3, and then that means your b value is 1 here. So then I'll go out 3 on my z-axis, and then 1 on my y-axis in both directions. Okay, so then now I want to make that central box. So this is where the central box actually is very super helpful, because if I don't have this, it kind of makes it hard to make your asymptotes so that your hyperbolas have an actual dimension. So here, from each of the vertices, I usually go out the same distance I did on the y-axis or the other axis. So whatever vertices axis is on. Okay, and then now you have a point here, a point here, a point here, and a point here. So now you want to connect it with the center, just making your hyperbola equation or asymptote lines. Okay? So now you've got your hyperbolas or your asymptote equations, so then you can create your hyperbolas. So just make them approach your asymptotes, give some good definition, and you guys probably make those look more 3D-ish. So now you've got 2 points here. So there's a negative 3, 0, 0, and a 3, 0, 0. And now you just need a third one, but that comes with the extension. So here, it might be easiest just to extend vertically. So let's go up 4. So 4, 4. Okay, so then now I can make the hyperbolas vertically, and then usually shading of some sort kind of helps your picture out a little bit. Okay, and you guys can do a better job of that, and then do the same thing over here for the top one. So okay, so then there's our equation. So now the reason why you want to wait for another point, because I don't want you to find a point like out here on the hyperbola. Just go with the vertices and that you extended vertically, because here, let's say this point, it still has the same x value, so it's still 3. It has the same y value because you didn't change that, so it's still 0. And then now, whatever value you moved it up, and it doesn't matter what your value is. You just need to pick one. Okay, so here I chose 4, so I would write 3, 0, 4, because that's how high I went up on my z-axis. Okay, so now I've got my 3 points on my hyperbolas. Okay. Then the next one, now just like I said, it could be any equation. So here you have z equals the sine of y. So then this is going to be a sinusoidal one. So let's go with your y-axis first. And remember, because you're talking about your y-axis and you're talking about sine, you want to change the scale. So you want to change it to radians so you can actually graph it. So then that means at 0, or sorry, at 0 for your y-axis, that means z is 0 as well for sine. At pi over 2 would be 1. Let's go make that up 1 and down -1 so we get a better picture. And then at pi it's 0, then 3 pi over 2 it's -1, and then 2 pi it's 0. And do the same for the other direction. Okay, so now you get your curve that you've seen lots of times from chapter 5 through 7. But now you want to extend it. Now we can label some of these points too. So you got 0, 0, 0. And you've got, let's say, pi over 2, comma, whoops, it would not be your x. So you'd say 0, comma, pi over 2, comma 1. Okay, so now extend it a certain distance, so let's go 3, just so it's not too long. Okay, and then extend your point so they touch. You get kind of the curve, and you can add some lines to give it some more depth or shade them. But now just extend out from one of your points, so like your 0, pi over 2, comma 1. Let's go to that point. So you went out on -4 in that direction, but it's still pi over 2 for your y, and it's still 1 for your x, or sorry, for your z. Okay, so those would be your graphs. Okay, so now just to give you a better sense of what those pictures should look like, I graphed those also on 3D Grapher. So the first one was the hyperbolic cylinder, so that's what kind of looks like, and then the sinusoidal one for 2b would look like the one on the right. And so it's got that wave and the extension on the all parallel to the x-axis. Okay, have fun.